Hello everyone. The title of this video is Solving Polynomial Equations Using Factoring. Now, every example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text in section 2.6 called Other Types of Equations, and I'm working under the heading Solving Equations Using Factoring. I threw the word polynomial in there because every example involves only polynomial equations. And yes, the examples I'm taking are either from the examples in this reading, or the try it problems in this reading, or from some of the exercises at the end of this section that are related to this particular objective. Now, I would ask that whenever I start a new example, that you pause the video and try to work it out yourself first before watching me do it and then comparing your work. Because I believe you should be practicing these things also on your own, instead of just watching me do them. Get more out of it. Alright, so each example I have written out on paper, and all we're asked to do is solve the equation, the polynomial equation, by factoring. And I've put out a video before on solving quadratic equations by factoring, right? And the quadratic equation is a type of polynomial equation, right? It's a degree 2 polynomial equation. So what we're going to be seeing in this video are some, just some higher degree polynomial equations. But I'm still going to be solving them in the same way that I solved quadratic equations by factoring. Right. So over here I'll put like some steps, right? The steps I'm going to be following. So for a polynomial equation, if I want to try solving by factoring, now that's not always the best method, but if I wish to attempt that method, first I would like to get the equation in the following form, where you have a polynomial on one side of the equal sign, and then the number 0 on the other. Right, so this particular equation here is not in this form yet, but I can very easily get it that way. We have 12 times x to the 4th power equals 3 times x squared. So what I'm going to do is I'm going to subtract the 3x squared from both sides. So minus 3x squared minus 3x squared. And now we'll have an equation that's in this particular form, right? And I personally, like to put the polynomials in descending order, by the power on the term. So the degree 4 term first, right, 12x to the 4th, and then the degree 2 term, minus 3x squared, equals, and then the other side is now 0. Right, so this is the way I want to get it to start. Right, then, take that polynomial and factor it completely. Right, so factor the polynomial completely. Alright, now again, I'm hoping you've either seen videos previously of mine on factoring polynomials and factoring techniques, or read through something from this particular text on factoring earlier in the chapter. So remember, the first step in factoring any expression is to find the greatest common factor, right, or the GCF of all the terms. Now for these two, 12x to the fourth and negative 3x squared, notice they both have a power of x, right? So the greatest common factor is going to have a power of x, and the power on x in the greatest common factor is the smallest of those powers that are in the terms. So x to the fourth, x squared, that's the smallest, x squared. And 12 and 3, or 12 and negative 3, the largest factor, common factor of those two is, 3. 3 goes into both those evenly. So I pull out this greatest common factor first. We have so 3 times x squared, that comes out. And then the remaining factor is just what's left over when I remove the greatest common factor. Now a quick way to find this is just divide each of these terms by 3x squared. So 12x to the fourth divided by 3x squared would be 4x squared. Minus, and then 3x squared divided by itself is 1. And then we still have equals 0. Now I'm not totally done yet. Right, I'm asking you to factor these polynomials completely. Now 3 doesn't factor any further, right? Any constant factors we'll just leave the way they are. X squared you could break down to x times x, but since it's the same factor twice, we're not going to get any new information. So I'll leave any factors that are linear factors to a power, I'll leave those the way they are as well. It's this expression here that can be factored further, right? 4x squared minus 1. This is actually a difference of squares, which again I'm assuming you know how to factor. Right? This is 2x to the second minus 1 to the second. So we have 3x squared, right? 3 times x squared times, and then 4x squared minus 1 factors to 2x minus 1 times 2x plus 1, right? Or 2x plus 1 times 2x minus 1. It doesn't matter what order the factors come in. Great. All right, so now I have done what I wanted. I've factored the polynomial completely. All right, and then once you've done this, you'll have a product, and here I have a product of like 4 factors, technically 5 because there's x times x here, but I have a product equal to 0. So then you're going to use or apply what's called the zero product property, which I'll refresh your memory of here, the zero product property, which, and I'll also be abbreviating this throughout the video as ZPP. Now the zero product property states that if a product of real numbers, and I'll just use 2 factors, it can be multiple more than 2 factors, but if a product of real numbers is equal to 0, or complex numbers even, go bigger, then one of those factors, either A or B or C, if there's a factor of C, whatever, then one of those factors, at least one of them, must be 0. Right, so either A equals 0, or this other factor of B equals 0, or both, And again, if there are multiple factors, if there's more than 2 factors, like I have in this question here, again, at least one of the factors must be 0 if a product is 0. Alright, so here, by the ZPP, right, by the zero product property, either 3 equals 0, but, not getting any information out of that, right? That's why I don't want to factor any numerical or constant factors, because you're not going to get any solutions from those. 3 equals 0, that's definitely false. You're not going to get any solutions from this, so I'm going to ignore that. Or x squared equals 0, right, this next factor. Now again, you could have broken this up to x equals 0 or x equals 0, right, if you did x times x for x squared, but either way, you're getting the fact that x has to be 0 here, but we'll get to that in a second. Or this next factor, 2x minus 1 equals 0. Finally, or this fourth factor, 2x plus 1 equals 0. Okay, so now I've applied the zero product property, and that gave me a few equations to solve. I started with this one polynomial equation, degree 4 quartic polynomial equation, and after factoring and applying the zero product property, right, I've transformed it in a way into 3 lower degree polynomial equations. So step 4 is solve the resulting equations. And then of course, last step in any equation solving is to check your solutions. And you always, and I've said this a bunch in other videos on equation solving, right, you always check back in the original equation, right? Check it back in the way that the equation was originally given to you. Alright, so 2x plus, here I have 2x plus 1 equals 0. That's, x would have to be negative 1/2. Or here I have x squared equals 0, and the only number really that you can square to get 0 is 0. So we have x equals 0 from that equation as a possible solution. Or, and then here add 1 divided by 2, x equals positive 1/2. And once again, don't forget, I'm not going to circle these yet. We're going to check them. Now the easiest one to check would be 0. Now I'm going to just do this mentally. When x equals 0, the left side of this equation is clearly 0. 12 times 0 to the 4th. And the right side of the equation is also 0. 3 times 0 squared, right? So you'd get 0 equals 0. So 0 works. I'm going to circle that one. And let's try a half. Now you're going to see that a half and negative half will basically act the same way because you're going to be raising them to even powers. Right on the right side it's squared, and the left side is to the 4th power. And when you take any real number to an even power, it's going to be positive anyway, right? So plug in a half. Now 1/2 to the 4th power would be 1/16. So we have 12/16, which is 3/4 on the left. And a half squared is 1/4, so you have 3/4 on the right. 3/4 equals 3/4. So 1/2 works, and the same thing would go for negative 1/2. You can check it on your own if you wish, but if I plug in negative 1/2, I'll also get 3/4 equals 3/4. Great. So this degree 4 equation has 3 solutions. Technically it has 4 because 0 would have counted twice, right? You had x squared equals 0, so that was x and x, right? So you'd have, this is what they would call a repeated solution, x equals 0. And then you have the half and negative half that were only counted once. But if you count how many times solutions repeat as well, the degree of a polynomial equation should be how many complex solutions you get. And remember, real numbers are complex, just with a 0 imaginary part. Great, so negative 1/2, 0, and positive 1/2. Excellent. And this is all I'm going to be doing for the entire video. Getting the equation in this form, right? Polynomial on one side, 0 on the other. Then using certain methods, whatever you recognize, hopefully you recognize how to factor the polynomial completely. Apply the zero product property to separate it into lesser degree equations. solve those resulting equations, and of course go back to the original one and check your solutions. Great. Next example. Alright, so the next example is a third degree equation, polynomial equation, or a cubic. So we have 3x cubed minus 6x squared minus 27x plus 54 equals 0. So this is already in that form that I want for a polynomial equation if I'm going to try solving it by factoring. Alright, everything on one side, 0 on the other. Alright, now notice that this polynomial has more than 3 terms. Alright, and you may recall when there are more than 3 terms in a polynomial, we're going to attempt, try something called factoring by grouping. Factoring by grouping. Try grouping. Now, factoring by grouping was, I'll just do this here. You have 4 terms. You can, you break up the polynomial into 2 groups. Now, a 4-term polynomial, you could break up into 3 terms and 1 term, or 1 term and 3 terms. But let's start off just cutting it in half. And I trust me, usually, depending on what text you're looking at, especially if it's an introductory algebra text like this one, usually a 4-term polynomial that could be factored by grouping, usually the best start is by cutting it into 2 groups of 2. So here comes the grouping part, right? So in one set of parentheses in one group, I'll put the first 2 terms, 3x cubed minus 6x squared, close the parentheses, right? There's one group. And then I personally like to put a big plus sign between my groups, right? Plus, and then I'm adding on the second group, which contains the second half, the next 2 terms, which are negative 27x and then positive 54. And then we still have the equals 0. Alright, then factoring by grouping. You break it into the 2 groups, and then you factor each group separately first by pulling out the greatest common factor of each group. The greatest or the opposite of the greatest common factor, we'll see that here. When the lead coefficient is negative, like it is in this second group with the negative 27x, when the lead coefficient is negative, pull out the opposite of the GCF. Trust me. Alright, so here, greatest common factor is 3x squared. And here, the greatest common factor is 27, right? But since the lead is negative in this group, since the lead coefficient is negative, we're going to pull out or factor out negative 27 instead, right? I'm going to pull out the opposite of the GCF. Alright, so for the first group, if I pull out 3x squared, the factor left over would be x minus 2. Alright, plus, and then this group here, I'm factoring out negative 27. And if you remove a factor of negative 27, you're left with x minus 2. Again, divide each of these by negative 27 to see what's left over. And if that factor left over after pulling out the GCF is the same for both groups, which you see here for both of these groups, it was x minus 2, then that means factoring by grouping will work. You can factor the polynomial by grouping. If they're not the same, then probably got to do something else. Alright. Oh, I guess I should have I do apologize. I should have pulled out a 3 from all these first, shouldn't I? Well, I can do that now. Sorry, the first step should be, remember, to take the GCF out of all the terms. So, well, let's just do that right now. So now that I've factored each group, let's factor the entire expression right now. There are two terms now, right? There are two products being added together. And the greatest common factor of these two products is, 3. This is where I'll pull out the 3, right here. 3 goes into 3, 3 goes into 27, so there's 3, and they both have this quantity, this factor of x minus 2. All right, so I'll remove that from both these terms. So we have 3 times the quantity x minus 2 times, and then when I remove this, you'd have just x squared in the first term, and pulling out a factor of 3 and x minus 2 here, you'd have minus 9, right? Now plus minus 9 is just minus 9. Right? Okay, so I'm almost done. Again, I should have pulled out this 3 in the beginning, so sorry. And then finally, we're not done yet. X squared minus 9 can factor even further, right? This is another difference of squares, x squared minus 3 squared. So we have 3 times the factor x minus 2 times, and then x squared minus 9 factors to x minus 3 times x plus 3. Great. All right, so that was step 2, right? Get the polynomial equals 0, factor completely. All right, factor completely. All right, and then I apply the zero product property, right? By the ZPP, I have a product equal to 0 here. Either 3 equals 0, but that's not happening, right? You're not getting anything from that, so I'm going to ignore that one. It's only the factors with variables that don't mean anything. That don't give me any information. Or, this second factor, x minus 2 equals 0, or the third factor there, x minus 3 equals 0, or the fourth factor here, x plus 3 equals 0. And then I solve these. Again, nothing coming from the factor of 3, right? But here, when x minus 2 equals 0, we get x equals 2. X minus 3 equals 0, we'd get x equals 3. X plus 3 equals 0, we'd get x equals negative 3. And now don't forget to check these numbers. Now you can use a calculator if you wish, but if I'm going to go back right to the original equation, there it is up top, start with 2, right? And I'll just do this first one, and I promise you the rest of them work. If you did everything correctly. Now 2 cubed is 8. 3 times 8 is 24. 2 squared is 4. 6 times 4 is 24. So you have 24 minus 24 right there. That's 0. And then negative 27 times 2 is negative 54. And negative 54 plus 54, that's also 0. So you get 0 plus 0 equals 0. 2 definitely works. All right. And 3 definitely works as well. I mean, this polynomial, is also equivalent to this one. And when I plug in 3, you just end up with 27 minus 27 equals 0. And when you plug in negative 3, you'd end up with negative 27 plus 27, also equals 0. So these work as well. Now again, you should be going back to the original, but anything equivalent to the original is also valid. Great. So again, we have 3 solutions, right? 2, 3, and negative 3. Wonderful. Yeah, so I'm going to be doing the same steps every time though, right? Polynomial equals 0. Factor the polynomial completely. Then use the zero product property, solve the resulting equations, check your solutions. Wonderful. All right, so the next example, very similar to number 2. X cubed plus 3x squared minus 25x minus 75 equals 0. So once again, I have it in the form that I want already. Right? If I'm going to try to solve it by factoring, got polynomial on one side, 0 on the other. And now I try factoring this, and once again we have a polynomial with more than 3 terms. So I'm going to attempt factoring. So first group, again, I'm just going to do 2 and 2. Again, 2 terms and 2 terms. So the first 2 terms, x cubed plus 3x squared in the first group, plus, and then the next 2 terms, negative 25x minus 75. And don't forget the equals 0. Then I factor each group separately. So the first group has a greatest common factor of x squared. And you'd be left with x plus 3 left over. Plus, now the greatest common factor of the second group is 25. But once again, the lead is negative. So I'm going to pull out negative 25. And if I remove negative 25 from this, what's left over would be x plus 3. And now look at these 2 terms, right? The whole thing as a whole, the 2 terms left over, the 2 products, they have this factor of x plus 3 left over, or in common, sorry. So the greatest common factor is this x plus 3. I pull that out. And then when I remove x plus 3, what's left over would be x squared plus negative 25, or x squared minus 25. And still not done, because x squared minus 25, hopefully you recognize that also as a difference of squares, x squared minus 5 squared. So that'll factor further as well. So we have x plus 3 as one factor, and then x squared minus 25 would factor to x minus 5 times x plus 5. And now I have what I want, right? A totally factored polynomial on one side equals 0, right? A product equal to 0. Alright, so I'm going to take this over here just because of my lack of space. By the 0 product property, right, ZPP, either x plus 3 equals 0, or x minus 5 equals 0, or x plus 5 equals 0. And solving each of these, we get x equals negative 3, or x equals positive 5, or x equals negative 5. And before I circle them, don't forget to check these solutions. So when x is negative 3, you're going to get, the first 2 terms will add to 0. It'll be negative 27 plus 27. And the next 2 terms will add to 0 as well. It'll be 75 minus 75. So you'd have 0 plus 0 equals 0. That's definitely true. And when x equals 5, these first 2 terms would add to 200. These next 2 terms would be negative 200. 200 minus 200 equals 0. And the same thing would, not the same thing. When x equals negative 5, these terms would add to negative 50. These terms would add to positive 50. So negative 50 plus 50 equals 0. That also works. But every single one of these works back in the original equation. So again, we have 3 solutions. Negative 3, 5, and negative 5 all work. Great. And I have one more example, right? All these are very similar. I had a couple where I did grouping. This one is actually more like example 1 I did. Now again, everything, this is a degree 5 polynomial equation, or a quintic equation. It's already set up the way I want, if I want to try factoring by solving by factoring. Polynomial on one side, 0 on the other. Now, I forgot to do this in number 2, and I apologize, but here remember the first thing you should look out for when factoring is the greatest common factor of all the terms. These have a GCF of 2x cubed. So I factor out 2 and x cubed. Now again, you can break up x cubed to x times x times x if you want, but as I had earlier in question 1, if you see in the same factor multiple times, just keep it as a power. Right? So instead of writing x times x times x, I'm going to leave it as x cubed because it's just the same factor over and over again. All right, and if I remove the factor of 2x cubed, you'll be left with x squared and then minus 7. Right? And we have equals 0. Now, this is completely factored over the integers. It is completely factored over the integers. Right? Now, when I say over the integers, that just means where all the coefficients are still integers, right? 1, 2, 3, -1, -2, -3, and so on. But you can factor this x squared minus 7 further over the real numbers, right, where all the coefficients are still real. So hopefully you can follow me here, right? 2 times x cubed. And if you want, x squared minus 7, you can factor as x minus the square root of 7 times x plus the square root of 7. Nothing wrong with that at all. Right, but now it's factored over the real numbers, right? Square root of 7 isn't an integer anymore. Right, and then so I could see people doing this, but if you want to stick to over the integers, we can stick to here. This polynomial, 2 times x cubed times x squared minus 7 like this. This is completely factored over the integers, and that's usually what people mean when they say factor things completely, is to factor them over the integers, right? So that all the coefficients are still integers. So then if I apply, the zero product property to this, we get, 2 is equal to either 2 is 0, but again, that's not giving me any information, or x is 0 and x is 0 and x is 0, but x cubed equals 0. Right? Again, you can break that up to 3 x's and write 3 different equations, but I'd rather just leave it as x cubed. Or, and then x squared minus 7 equals 0, right? This factor here. And then you solve these. Now the only number you can raise to any non-zero power and get 0 is 0 itself, so we're getting x equals 0 from this one. And then this equation is a quadratic equation that you can solve with the quadratic formula. You can solve it with the square root property, though, right? If I add 7 to both sides, we get x squared equals 7. And then by the square root property, which I've brought up in previous videos, right? So I'm not going to do that here. X is either going to be equal to the square root of 7 or the negative square root of 7. Right? What you would have gotten if you factored it completely over the reals, like I did here, and then applied the zero product property, you would have gotten positive square root of 7 from this factor and negative square root of 7 from that factor. And then don't forget to check. Right? Don't forget to check. So 0 is obvious, right? 2 times 0 minus 14 times 0. You get 0 minus 0 equals 0. Wonderful. All right, now the square root of 7 maybe isn't as obvious. The square root of 7 to the 4th power would be 49. 2 times 49 is 90. You have 98 times the square root of 7 for the first term. Square root of 7 to the 3rd power would be 7 root 7. 7 times 14 is 98 again. So you'd have 98 times the square root of 7 minus 98 times the square root of 7. This works. And negative square root of 7 would just do the opposite. You'd have negative 98 times the square root of 7 plus 98 times the square root of 7 equals 0. So both those work. Now if you want to use technology, let me show you. I've brought this up as well in previous videos how I like to use technology calculator to check solutions to equations. I have a TI-84 Plus emulator. If you have TI-83, 84, you know, both are pretty much the same. So if I wanted to check, the square root of 7 in this equation here, I'll type in, the square root of 7, and then store it as x. So I had the stow button and then x. So now whenever I hit the x button, it's the square root of 7. See, x is is the square root of 7. And then I go back to the equation and I punch in the expressions on both sides. Now, only the expressions with variables though, so I'm only going to punch in the left expression and see if I get the right side, see if I get 0. So the left expression was 2 times, x, and remember, whenever I hit x now, it represents the square root of 7. So 2 times x, to the 5th power, 2 times the square root of 7 to the 5th, minus 14 times x to the 3rd. And I hope I get 0. And I do. Excellent. Excellent. Alright, so that means the square root of 7 is a solution to this. And the same thing would go, and I'll leave it to you if you have a calculator that's capable of this. Put in negative square root of 7. Now you don't have to store it as a variable. I mean, you could just type in 2 times negative root 7 to the 5th minus 14 times negative root 7 to the 3rd. It would just take a little longer. And see if you get 0 back. And you should. You should, right? They both should work out. So excellent. This has, 3 solutions. Again, I said earlier, this is a degree 5 equation. So it should have 5 complex solutions. And it does, technically. Negative root 7, positive root 7, and then 0 and 0 and 0, right? There was x cubed here. This is one of those repeated solutions. And it would repeat, 3 times. There were 3 factors of x. So 0, 0, 0, square root of 7, negative square root of 7. There's your 5 complex solutions for this degree 5 polynomial equation. But that's it. All right, those are all the examples I've pulled from this text. There are others for you to practice on your own, of course. But just doing the same thing every time here, right? Getting polynomial equals 0, factoring that polynomial completely, and applying the zero product property, solving the resulting equations, checking my solutions. Wonderful. And I'm hoping that watching me go through these 4 examples here, help you in some way when you're asked to solve a polynomial equation by factoring on your own. And thank you very much for watching.